Right now, as you listen to these words, something is happening that you have never once questioned. Time is passing. The moment that just was is now gone. The moment that is coming has not yet arrived. And you, here, in this thin sliver of the present, are moving through time in one direction only. Forward. Always forward. Never backward. Never sideways. Never still. This feels so obvious that stating it seems almost meaningless. Of course time passes. Of course the past is gone. Of course you cannot return to yesterday or skip ahead to tomorrow. This is simply how reality works. This is the most basic, most universal, most undeniable feature of human existence. And yet, when physicists look at the equations that describe the fundamental workings of the universe, the equations of quantum mechanics and general relativity that govern everything from the behavior of subatomic particles to the movement of galaxies, they find something profoundly strange. Time does not appear in those equations the way you experience it. The past does not disappear. The future is not unwritten. The distinction between what was, what is, and what will be, the distinction that feels more certain than anything else in your entire experience of reality, is not written into the fundamental laws of physics, which raises a question that is simple to ask and almost impossible to answer. What is time? Not as a practical matter, not as a clock or a calendar, but as a feature of reality itself. Does time flow, or does it only seem to? Is the present moment genuinely special, or is it just the point where your consciousness happens to be sitting right now? These are not idle philosophical questions. They're among the most seriously debated problems in modern physics, and the answers, unsettling as some of them are, change everything about how you understand your place in the universe. Settle in, pour your tea, and let us think about this together. To understand the strange physics of time, we need to begin with the most successful and most disorienting theory in the history of science, Albert Einstein's theory of relativity, specifically the special theory of relativity published in 1905, and the general theory that followed in 1915. Before Einstein, time was simple, or at least it seemed to be. Isaac Newton, whose laws of motion governed scientific thought for over 2 centuries, described time as absolute, universal, the same everywhere, a single cosmic clock ticking away identically for every observer in every location throughout the universe. You had your clock and I had my clock, and though we might be far apart and moving differently, our clocks would tick at the same rate. Time was the same for all of us. It was the backdrop against which everything happened, reliable, fixed, unquestionable. Einstein dismantled this picture entirely. What he showed through mathematical argument that has since been confirmed by experiment after experiment is that time is not absolute. Time is relative, and the rate at which time passes depends on 2 things that Newton never considered. The first is velocity. The faster you move through space, the slower you move through time. This is not a metaphor. It is not an approximation. It is a precise, measurable physical fact. An atomic clock placed aboard a fast-moving aircraft ticks slightly slower than an identical clock left on the ground. The clocks are measuring the same physical process, but time itself is passing at different rates for the 2 clocks because they are moving at different speeds. The second is gravity. The stronger the gravitational field you are in, the slower time passes for you. A clock at sea level, deeper in Earth's gravitational well, ticks slightly slower than a clock at the top of a mountain. The difference is tiny in everyday human experience, but it is real, And for the GPS satellites orbiting Earth, which are both moving fast and sitting in weaker gravity, the time difference is significant enough that if engineers did not account for it, GPS navigation would accumulate errors of kilometers per day. Relativity is not theory, it is engineering. We use it every time we navigate. But relativity does something more philosophically radical than simply telling us that clocks tick at different rates. It tells us that the very concept of simultaneity, of two events happening at the same time, is not absolute. Whether two events happen simultaneously to one person may appear to happen at different times to another person moving at a different velocity. Neither observer is wrong, neither is making an error. They are simply in different states of motion, and in different states of motion, time itself is different. And this leads to a conclusion that Einstein himself described as deeply troubling. If simultaneity is not absolute, if there is no universal now, then the idea of the present moment as a special, unique, privileged slice of time is an illusion, or at least it is not a feature of the universe, it is a feature of the observer. This insight leads directly to what physicists call the block universe, or more formally, eternalism. The block universe is a way of thinking about time that follows almost inevitably from the equations of relativity, and it is profoundly strange. In the block universe picture, the past, present, and future all exist simultaneously, not sequentially, not one after another, but all at once in a four-dimensional structure that physicists call space-time. Think of it this way. You are used to thinking of the universe as three-dimensional space in which things change over time. The present is real, the past was real but is now gone, the future will be real but does not yet exist. In the block universe picture, all of that is wrong. The universe is four-dimensional, and time is the fourth dimension, not fundamentally different from the three spatial dimensions we can move through, but another axis of the structure of reality. The past exists in the same sense that distant space exists. The future exists in the same sense that a location you have not yet traveled to exists. You do not think of a city in another country as not real simply because you are not at that location yet. In the block universe, 1905 still exists. The year 2200 already exists. You as a child exists. You in the last moments of your life exists, not as memories or echoes, but as actual, real, existing states of the universe, simply located at different coordinates in the four-dimensional structure of space-time. The experience of time passing, of moving from the past through the present into the future, is not time itself. It is your consciousness moving along the time dimension of the block universe, the way your eyes move along a line of text. The text was all there before you started reading. The reading did not create the words, it just traversed them. Now, I want to pause here and sit with what this actually means, because the block universe is not just a technical claim about physics, it is a claim about reality that touches everything. If the block universe is correct, then the moment you were born still exists. Right now, in the full four-dimensional structure of space-time, the day you were 5 years old is as real and present as this moment. Every person you have lost is still there, not as a memory, not as an echo, but as a real state of the universe, located at a different point in space-time than where you are now, but just as actual. And every moment you have not yet lived also already exists. Your future, whatever it contains, is not being written. It is already written. You are moving through it, but it is already there. This is the view that follows from the most successful physical theory in history, and it is not comfortable. It raises questions that physics does not answer, and perhaps cannot answer. If the future already exists, is free will an illusion? If you cannot change what is already real, can you make genuine choices? If the past never truly disappears, what is loss, really? What is grief? These are not easy answers, and I'm not going to pretend they are, but I think they are worth sitting with, because the discomfort of a genuinely deep question is always more valuable than the comfort of a shallow one. But let us complicate the picture further. Because the block universe, compelling as it is not the only thing physics has to say about time. There is another mystery, one that points in a completely different direction. The equations of physics, including the equations of relativity, are time-symmetric. This is a technical phrase that means something important. The equations work equally well in both directions of time. If you filmed any physical process and played the film backwards, the reversed process would also be consistent with the laws of physics. A ball rolling across a floor, an atom emitting light, two particles colliding. All of these processes, run in reverse, describe something that is physically possible. The laws of physics do not distinguish between past and future. And yet, your experience of time is radically asymmetric. You remember the past, you do not remember the future. Eggs break, but do not unbreak. Coffee cools, but does not spontaneously heat back up. People age in one direction only. Why? If the laws of physics are time-symmetric, if the equations do not care which direction time runs, why does time have an arrow? Why does it feel so unmistakably like it only flows one way? The answer most physicists favor involves something called entropy, a measure of disorder in a system, and a law, the second law of thermodynamics, which states that entropy in a closed system tends to increase over time. Disorder increases. Things fall apart. Order requires effort to maintain and dissipates without it. And this increase in entropy, this relentless tendency toward disorder, is what gives time its direction. The past is the direction of lower entropy. The future is the direction of higher entropy. But this answer, satisfying as it is in some ways, simply pushes the question back further. Why was entropy so low to begin with? Why did the universe start in such an extraordinarily ordered state that everything since has been moving toward greater disorder? The honest answer is, we do not fully know. The origin of time's arrow, the reason the universe has a direction, remains one of the deepest unsolved problems in physics. It sits at the intersection of thermodynamics, cosmology, and quantum mechanics. Brilliant people have been working on it for over a century, and it is still open. There is one more idea I want to share before we close, one that is perhaps the most radical of all. Some physicists, taking seriously the equations of quantum gravity and the foundations of quantum mechanics, have arrived at a position that seems almost impossible. Time may not be fundamental at all. In certain approaches to quantum gravity, the attempt to unify general relativity with quantum mechanics into a single coherent theory, time drops out of the fundamental equations entirely. It does not appear as a basic feature of reality. It emerges. It is something that arises from deeper, timeless structures in the universe. The way temperature arises from the collective motion of molecules, not existing at the level of individual particles, but appearing as a large-scale feature of many particles together. The physicist Carlo Rovelli, who has written more beautifully about this than almost anyone, describes time as something that disappears when you look at the universe at its most fundamental level. At that level, there is no before and after, no flow, no passage, only relations between things, only a network of events connected to each other. What we experience as time, the passage, the flow, the irreversible movement from past to future, is something that emerges for beings like us, complex, warm, entropy-producing creatures whose experience of the universe is necessarily limited by our scale and our perspective. We are not standing outside of time looking at it objectively. We are inside it. We are made of it. And our experience of its flow is real, but it may not be a fundamental feature of the universe. It may be a feature of what it is like to be us. Before you leave this moment, I want to offer you one question to carry. If every moment you have ever lived still exists, real and present somewhere in the four-dimensional structure of space-time, what does that change about how you feel about the moments you have lost? And if the present moment is the only one you are directly inhabiting, the only point in the block universe where your consciousness actually sits, what does that suggest about how you might want to treat it? Time may be stranger than anything you imagined, more uncertain than any clock can measure, more mysterious than any calendar can contain. But this moment, right now, is undeniably real, however you understand what it is, however the physics eventually resolves. It is here, you are here, and that, whatever time turns out to be, is not nothing. This is Green Tea English. Thank you for thinking with me today. See you in the next one.